In this video, I'm going to talk about the Newton's second law. This is how we describe the Newton's second law of motion for a system. We say that time rate of change of the linear momentum of the system is equal to sum of the external forces acting on the system. So the momentum, so we say momentum, right? So what is momentum? The momentum is mass times velocity. So mass times velocity is the momentum. And let's consider a small particle. So then the mass of the small particle gonna be rho dv, right? And then the momentum gonna be the velocity, right, times this mass. So then this is gonna be the momentum of a small particle, right? And then uh, this is also, this formula right here is the momentum of the entire system of the fluid, right? Of the system, sorry, of the system. And this formula is valid for an inertial coordinate system. For instance, fixed coordinate system is inertial, a coordinate system that moves in a straight line with constant velocity, of course, and without acceleration is also inertial. So we proceed to develop the control volume formula for the important law. By applying the Reynolds transport theorem and using B of the system as mv, then the small b gonna be v, right? If we use that one, this is the formula that we derive out of the Reynolds transport theorem by considering the B system and B like mv and v. And we also call this, if I want to elaborate all of the terms in this formula, this whole thing we can call it, let's first just, okay, let me do something else. So this one right here, this is time rate of change of the linear momentum of the system. Okay, of the system. Oops. Of the system, and this one right here is the time rate of, again, change of the linear momentum of the content of the control volume. And also these terms here, so and also these terms here is the net rate of flow of linear momentum through the control surface, which is also, we can say all of these, meaning the change in linear momentum through control volume, right? And also we can say that by considering the Newton's second law, we can say that this is equal to sigma of the force of control volume. And the forces on control volume is we consider the body force and the surface forces. So if I want to elaborate that and by showing these two pictures, okay, let me just okay, let's look at this picture right here. So we have weight here, which is our body force. We have these two forces here, which are the surface forces, and also we have this wall effect right here. So if I want to just write it down, we're gonna have, okay, we're gonna have body force so in which the only body force that we consider is the body force of weight. So let's write down weight. And the surface forces are kind of basically exerted on the contents of the control volume. For example, we have wall effects. So let's say we have this, this is the dash line is our control volume. Let me just show you the dash line is our control volume, means the fluid inside the pipe, right? So let's write it down, the fluid inside the pipe. So if we consider this control volume, so we have some wall effect of the pipe on the fluid, and so if I just draw some forces here, these are the shear stress, right? And also let's consider the pressure over wall. Oops. pressure over wall, and again we also have the shear stress on the bottom part of our figure, right here. And also what else we have? Yes, the other one that we have is pressure effect. Give me a second, please. Okay, the other one that we have is the pressure effect. And the pressure effects, if we want to look at the surface of our control volume at the end and at the beginning of the type. So if we consider here, we have P1 right here, and also we have P2 right here. So this is P, and then let me just write it down. This is the shear stress at wall reaction of pipe on fluid. And if we combine all of the forces together, we're gonna get P of wall plus 2 of wall, and they are not forces, right? They are pressures, so we need to multiply them by the area of the wall. And this is gonna be, this is going to be our, because we have x and y direction in this question, in this figure, so this is all the forces that we have, right? I mean, not all of the forces, just combining the pressure and shear stress. So this is the combined wall effects from pressure and shear stress. So this formula, right? So just be careful that this pressure right here is, oh my god, okay, this pressure right here is at the opening. And we also know that the weight we can, okay, let me just, I forgot to show it on the picture. So this is also weight, and we know that the weight, which is the weight of fluid, is gamma times area. And just some side notes on how to approach for to solve the question. First, we need to identify a control volume like what we had here, the dashed lines. And then we need to also identify the coordinate system, which shows I mean, like just something simple, like this is x and this is y, and then because when we want to use the forces, we know that what is the direction. And then we also need to consider all of the possible assumptions that we can have. For example, we can assume this is a steady state. It means that there is no variation over time. And I mean, it depends on the problem. Some of them is not a steady state, but um, not most of them. Maybe, yeah, maybe most of them in this class is going to be considered as a steady state, but not always. And then we're also gonna consider the constant properties and the one-dimensional flow. So for one-dimensional flow, I mean that, for example, means the uniform velocity, and the uniform velocity, if we want to look at the picture right here, this is the uniform velocity, and this is not the uniform velocity. For example, here the average is equal to, if we say that this is u, this is equal to the average of velocity. So this is why it's uniform. And then let me also talk about these notes here. We say that the linear momentum is directional. What it means is that, for example, we have this formula that we got from the Reynolds transport theorem, right? This is CS V rho V dot N dA, right? This V right here this is refer to direction of flow and its components. However, these terms here, we show that, for example, if this is the surface, if V is going in and the normal is also perpendicular to the surface, then if we consider the product, it's negative when it's in flow and it's positive when it's outflow, right? And for talking about that that one-dimensional flow, let's see, we have some pipe like that, and I have a velocity right here, and also I have the normal right here, and this is our theta. So if we consider that one, our V is equal to Vxi plus Vyj, right? And what is Vx? We can look at the figure, and we have theta here, right? So V is gonna be minus V times cosine theta, because if I consider the x, my coordinate system, this is going to be V cosine theta, and because it's in the opposite direction of the positive x, it's going to be negative. And then this is Vy right here, going to be equal to V times sine theta. And also now if I consider this formula, which is our linear momentum, the part of a linear momentum. So we have Vx here for the x direction. So for the x direction, this is why we say that the linear momentum is directional, right? So x direction, we're going to consider x direction, and we are going to consider y direction. Okay, let me just clean it a little bit. Let's put this coordinate system right here, and also bring it a little bit here. Oops. Okay. Now in x direction, and in y direction. So in x direction we have Vx, right, for this one, and for rho Vn we have rho Va. And also for the y direction we have Vy and rho Va. And we know that rho Va is m dot, which is mass flow rate. So then it means that we can also say Vx dot m dot, and for y direction we have Vy dot m dot. And also we need to have our if we want to consider the average of velocity, this is how we get that, because this V right here is the average of velocity, right? So this is how we are going to find the average of velocity. So I'm going to solve some question on the linear momentum in the office hours.